Okay, so before we get into the following chapters, namely torsion, bending, transverse shear, all that good stuff, I want to clear up this concept of what a moment of inertia is and the different moments of inertia and what they mean conceptually. Because when I did this, I had no idea what this stuff meant, right? So we're gonna go over that because I do not want to explain it every single explanation going forward, yeah? Because it is important to understand what they mean. So we're gonna go over three different ones. One of them does not concern us in this course, but it'll help us with the explanation of the following too, right? There's also one more, but I don't know if we'll explain it today. Regardless, we'll get into it. So the first moment of inertia we're going to go into, or we're going to talk about, is the mass moment of inertia, right? And this is probably the one you're most familiar with. You may have done it, or you should have done it in first year physics, or depends where you did high school, but high school physics, or dynamics, namely, right? Mass moment of inertia. And what does this moment of inertia describe? Well, it describes rotation, right? Or resistance to rotation. Resistance to rotation about an axis. To rotation about an axis. About an axis. Okay. And it's typically represented, if you're talking about the x-axis, again, you could do it about any axis, but if you're talking about the x-axis, ix, iy, iz, you get the point. Okay. How do I know, firstly, just conceptually, how do I know it represents the resistance to rotation about an axis? Well, let's look at a formula that uses the mass moment of inertia and try and understand it. But before we even get to that, let's look at a formula before that, right? And that is our good buddy, F is equal to ma, right? Force is equal to mass times acceleration. What is mass in this case? Well, mass, I can say, is a resistance to acceleration, or is a resistance to motion, right? Because if I have a mass, and I apply a force to it, and this is accelerating, the heavier my mass is, the more resistance there is to my system to accelerate, right? The more resistance it provides to this box to stop acceleration, right? To stop motion, right? Because the heavier it is, the more resistance there is to acceleration, right? So I have to apply a harder force, right? So hopefully that concept is understood, that in this equation, if you look at it, mass is resisting acceleration. Okay. Let's look at a similar formula, the angular version of this formula. I know that torque is equal to the mass moment of inertia multiplied by an angular acceleration. Okay, what the heck does that mean? Well, if I have, how am I going to draw this? Let's say this is my z-axis. This is my x. This is my y. Plus x plus y plus z. And let's say I have a slender rod, a rod like so. Okay, let's say torque is equal to that. Say I have a slender rod like so. Hopefully that drawing isn't too bad. Okay. Let's say I apply a torque about the z-axis, right? I apply a torque about the z-axis. Therefore, my rod is accelerating angularly, has an angular acceleration about the z-axis. And for this formula, therefore, torque is equal to the moment of inertia, the mass moment of inertia of the z-axis multiplied by the angular acceleration, right? Hopefully this system makes sense. Okay. The same way that force is equal to ma, the same way that mass was opposing my acceleration, the greater my mass was, the less acceleration I would have. Similarly, the greater my mass moment of inertia is in the z-axis or about the z-axis, the less angular acceleration I have, right? So it's opposing, it's resisting, the same way mass is resisting acceleration or linear acceleration or motion, if you look at its core, the mass moment of inertia is resisting rotation, right? It's resisting rotation and it's resisting angular acceleration. So hopefully that kind of made sense. So long story short, the mass moment of inertia resists rotation about an axis. It is a resistance. It is a measure of resistance to rotation. Okay, hopefully that was understood. How do we represent it? Well, in mechanics, we don't really care. We just care about this concept that it's a resistance to rotation. But we'll kind of explain it. I won't go over it because that's the job for dynamics or even Calc 3, because if you're talking about 2D And for example, we'll talk about the x-axis, right? If we're going to talk about the moment of inertia, or the mass moment of inertia, about the x-axis, it's equal to, in 2D, it's equal to y squared multiplied by a differential mass element, right? A very small mass element, right? And again, this is reliant upon mass, right? Okay. In 3D, it's equal to Ix is equal to, if I remember correctly, it's equal to, you could get a triple integral. I don't remember. I think it's y squared plus z squared dm. And then this translates to eventually a triple integral y squared plus z squared multiplied by mass density function dv. But I don't know, this might be wrong. But long story short, these are the formulas that represent it. And typically you don't even need to go over this stuff unless you're doing like the derivations or Calc 3. But long story short, the whole point of discussing this part was I want to extract that the mass moment of inertia is a resistance to rotation about an axis, right? Okay, hopefully that makes sense. Now we're going to talk about a different moment of inertia, which we're going to deal with, which we're directly going to deal with in Chapter 6 and going forward. And Chapter 6 is bending. So this other moment of inertia is called the area moment of inertia, or the second moment of inertia, right? We'll call it the area moment of inertia. The area moment of inertia, or the second moment of area. It's also called second moment of area. What does this one represent? Well, again, I said we use this one in mechanics and materials. Do we have any rotation? Do we have any motion in mechanics and materials or statics? Well, no, we don't. We only have like small deformations or deflections. So consequently, this isn't a measure of the resistance to rotation, but about an axis, it's a measure of a resistance to bending about an axis, right? So it's a resistance to bending about an axis. About an axis. Right? Okay. So how do we represent the area moment of inertia in terms of symbols? Well, we represent it via IXX if we're talking about bending about the x-axis, right? Or IYY. And we'll get to IZZ in just a second. But this is how it's typically represented. There may be other forms, right? Okay, let's do an example of how to find IXX. And we'll do the... we're just doing 2D cases, right? Because we don't really care about 3D in our scope of things. So we're going to do 2D cases. IXX is going to equal to, very similarly, instead of the integral of y squared dm, we have dA, right? Because the mass moment of inertia, it depends on the distribution, for the 2D case, the distribution of mass in a cross-section, right? How the mass is distributed within a cross-section. The area moment of inertia, very similar, but we're talking about the distribution of area within a cross-section, right? And we'll get to that in just a second. IYY is equal to the integral of x squared dA, right? Okay, let's try and find the area moment of inertia about the x-axis for bending of, let's say, just a typical beam or a typical rectangle, if we're going to really simplify things, right? This is kind of how it's going to look like that, plus y, plus x, and we're going to bend it about the x-axis like that, right? And we'll call this distance right here, from here to here. We'll call this distance b, the base of the rectangle, and we'll call this distance right here h, the height of the rectangle, right? And we want to find the area moment of inertia about the x-axis for bending about the x-axis. And if you can't visualize it, if you look at it from the side like this, the z-axis is coming out at you, right? And you're bending it about the x-axis. If you look at it from the side, from the right side like this, you're going to see that you're going to have your y coordinate. Your z is going to come out. and then you're kind of bending it about the x-axis like that, right? And this is the x-axis coming out at you. So this is bending about the x-axis, right? So we want to find the resistance of bending about the x-axis, and that is the area moment of inertia about the x-axis. Long story short, I'm going to tell you the punchline. We're going to end up getting, from doing this calculation, we're going to end up getting that Ixx for this shape about the x-axis is equal to BH cubed over 12. To my knowledge, in statics, we do all this, like if you took a dedicated statics course, you have to like know how to do this derivation. But for our cases in mechanics, we're past statics at this point. We just care about memorizing this one, right? Similar to dynamics, you wouldn't have to memorize, for example, a slender rod, like the rotation about a slender rod about its z-axis, like that. You wouldn't have to know it's 1 over 3 or 1 over 12 ml squared. You wouldn't have to know how to derive that, right, necessarily. You just memorize it, right? Or it might be given to you on a formula sheet, right? So that's all we care about at this point. We just care about getting it. But if you want to know how to derive, we're going to go through that. If you don't, skip ahead a bit, right? Okay, how do I get from this formula to this formula, right? Well, I'm going to say that my differential A, this basically says that y squared multiplied by a differential element A, and then I take the sum of that, and then I'll get my area moment of inertia. I'm rambling. Let me get to the point. Okay, we have this differential A, right? A very, very small piece. This very small area A, right? And I'll color it in. This is called dA. How can I represent dA? And it's a distance y from the x-axis, right? How can I represent dA in a different way, right? I can say that it is this length b multiplied by a differential length dy, right? Let me repeat that. This entire rectangle is made up of infinite amount of slices, dA, right? And each of them, this is a slice, y, each of them have a length b and a height dy, right? And let's take another slice, for example. This would be negative y, or y, doesn't matter. And then you also have a slice here. So we're going to have an infinite amount of slices. Again, this is dy. This has a length dy, a very, very small length in the y direction, multiplied by b. So if I take the integral of all of these dAs, right, because dA is equal to b times dy, I'm going to get the full area, right? If I take an integral of this, I'm going to get the full area, right? I'm going to get this entire area, right? So that's basically what we do for this guy. So Ixx is equal to the integral of y squared dA. Again, what did I say? We can replace dA with this differential slice. I can replace it with the length b multiplied by dy, right? Just base times height. I'm going to say that this is equal to the integral of y squared multiplied by b dy. I'm going to keep going. I'm going to take b out of the integral because it does not, like, it doesn't matter. dy, right? What are my bounds of integration? Well, I'm taking dy from negative h over 2 to positive h over 2, right? So those are my bounds of integration. I'm taking all these infinitesimal slices, or these heights, from here all the way to here. And this is negative h over 2 and h over 2. What you're going to end up getting is b y cubed over 3 is equal to, or in the bounds is h over 2, negative h over 2. You're going to keep going. You're going to get that b is equal to, once you plug everything in, you're going to get the exact same thing that we have. So this is basically how you apply this integral formula to find this moment of inertia, or this area moment of inertia. But yeah, the y direction, it's almost the exact same thing. And if you actually want to do it, I'm not going to do it, but if you want to do it, you're going to end up getting just this switched, right? Ix Iyy is equal to b cubed h over 12, right? If we bend it about the y-axis, you're going to get this lovely guy as your resistance to bending about the y-axis, right? And that should actually make sense, but if I start going into it, I'm gonna like spend another 20 minutes talking about it. So let's not do that. Okay, so that sums up the area moment of inertia, or what I wanted to talk about when it comes to the area moment of inertia. We did the derivation, we explained what it means conceptually. Great stuff. There is one side topic, we'll call it 2A, and that is called the first moment of area. This one, it doesn't really have any like specific, to my knowledge, it doesn't have any like necessary meaning, like when it comes to like a conceptual meaning, like resistance to bending or resistance to something like that. But it helps us find, and it's represented typically by Qx or Qy. It basically helps us find the centroid, the center of area, right, of a shape, right, or the neutral axis, or something like that. I think we find the neutral axis using, if you divide it by the total area, you'll find the neutral axis. But we'll get to that in the future when we talk about bending. But if you do want to know the formula for this good guy, for example, Qx is equal to, very similar to the second moment of area, it's equal to the integral of y dA, and then Qy is equal to the integral of x dA, right? So, but we'll talk about that later when we talk about bending, right? So that does not concern us right now. Okay, I think we're done with the area moment of inertia. We're going to talk about the last and third topic, and that is the polar moment of inertia. Let me just make this a bit smaller. That's the polar moment of inertia, right? So we'll call this 3. Polar moment of inertia. Okay, what does this one represent? Well, this one, if we say the first moment for the first mass moment of inertia, it represented a resistance to rotation about an axis. The area moment of inertia represented a resistance to bending about an axis. Well, the good old polar moment of inertia represents a resistance to torsion loading or torsional loading about an axis, right? Represents, or I don't even need to say represents resistance to torsional loading. Loading about an axis. And in this case, an axis perpendicular to the cross section, but we'll get to that. About an axis. Okay, it's typically represented by J, but it's also represented by IZZ. Remember when I said that we're going to get back to IZZ later? Well, this is what I was talking about. Okay, so if we draw a coordinate system, I think the best way to explain this is via a coordinate system. This is your plus y, this is your plus x, and please remember your z is coming out at you. It's coming out of you or going into the page, right? Let's deal with a circular cross-section because that's normally what we do in torsion. Right? And from this, let's say we add a torque to this circular cross-section. How am I going to add a torque? How am I going to twist it? How am I going to basically, I don't want to say bend it, but this is basically torsion, right? I'm twisting it like this, right? If I had a bar like that, I'm twisting the bar, right? About, if you look at it, if you try and visualize it, pretend this is the axis going through the middle of your bar. You're twisting it about that axis, and that is torsion, right? You're applying this torque, right? You're trying to deform it, you're trying to twist it, right? And that's basically what we're doing. So the polar moment of inertia, it represents the resistance to torsion about for a cross section, right? And what axis am I trying to twist it about? Well, it's the axis that's coming out at me, right? It's coming out at me. This is the z-axis, right? So I'm trying to twist it about that axis. I'm trying to twist this cross section about that axis, and J represents the resistance to this torsion, right? Okay. How do we end up doing it? Well, this is a circular cross section, so it's much easier for me to use cylindrical coordinates. We're going to end up getting, and I'll give you the formula, and we'll do the exact same thing like we did before, right? You're just expected to know this formula. J is equal to pi over 4 for this example, or pi over 2, r cubed, or r to the fourth power, and we'll call it capital R, where r represents the radius of our circular cross section. But if we wanted to actually do the integral version, in this case, we're going to get that our polar moment of inertia is equal to the integral of r squared dA, right? Okay, again, how do I get from here to here? We're already done with the conceptual stuff. Let's do like the derivation kind of. Okay, well, let's make this a bit smaller. Amazing stuff. Okay, make this a bit smaller. Okay. So, let's say that my radius comes out like this, right? Any given radius. I want to find my differential area. I want to be able to do this integral, but I need to clarify what my bounds are, and I need to convert this to cylindrical coordinates, basically, right? Okay. If this is my area, this differential area A, dA, right? How can I represent this in a different way, right? Well, I can represent this, if this is theta and this is r, I can represent this differential area, and let's zoom in like this. Let's make it bigger. I can represent this differential area dA by this distance. I can make it like a small little rectangle. This distance will be d theta, right? A small theta multiplied by a small radius, right? And it's just length times height, right? So that's how we end up doing it. And basically, if you didn't want this explanation, what we're doing in essence is just converting to cylindrical coordinates, and that makes this instead a double integral. R squared, what do we replace dA with? Always when you're converting to cylindrical, it's r dr d theta. R dr d theta. What are your bounds? Well, I'm going from for my r bounds, for my radius bounds, I'm going from 0 all the way to r, right? I'm integrating across this space. And then for my theta bounds, I'm integrating from 0 radians to 2 pi radians, right, for the entire circle. And then from this, it becomes a very simple integral. You go from 0 to r, 0 to 2 pi, r cubed dr d theta. Once you end up doing this lovely guy, you're going to end up getting what we have. J is equal to pi over 2 r to the fourth power. But something that's kind of cool is that if I come back here, and this is another definition for the polar moment of inertia, if I come back to this formula and I zoom in on it, I say IZZ is equal, and it's equal to J, remember, whatever, it's equal to r squared dA, right? I know that if this is r squared, this is x squared, and this is y squared, right? So I can say that r squared is equal to x squared plus y squared, right? Okay, let's replace that. This is equal to the integral of x squared plus y squared dA, right? Let's keep simplifying. Let's split up this integral. I can say that IZZ is equal to the integral of x squared dA plus the integral of y squared dA, and hopefully you can see it by now. I can say that IZZ is equal to, does this not look familiar? The integral of x squared dA. Well, that's simply the area moment of inertia in the y direction, or about the y-axis. And what's the integral of y squared dA? Well, it's simply the area moment of inertia for or about the x-axis, right? So I can replace that. I can say, therefore, I have another definition for the polar moment of inertia. I can say that IZZ, the polar moment of inertia, in this case, and remember, it's not always IZZ is the polar moment of inertia. Like, imagine this was z and this was x, right? That makes y my axis that is perpendicular to my cross section, right? So it's variable, right? Okay. What do we say? This is I y y plus I x x, right? So we have different ways that we can find the polar moments of inertia, but that's basically, I think, a summary of all the derivations you can do. And that, I think, includes this lovely video explanation, where basically a summary is we have different types of moments of inertia. I have no idea why they named them like this. I don't even think this is supposed to be called the area moment of inertia. I think second moment of area is a proper name, from what I remember when I learned. But yeah, the polar moment of inertia represents a resistance to torsion, right? To torsional loading about an axis perpendicular to your cross section, and we're talking about 2D, remember that? The area moment of inertia represents a resistance to bending about an axis, and the mass moment of inertia, you'll probably do in dynamics or another course, I don't know, or many courses actually in the future, where we're dealing with rigid body rotation, and it represents the resistance to rotation about an axis. Hopefully this was helpful, and we will get into the following chapters.